Hi, everyone. Welcome back from the break. I hope you're caffeinated and ready for the next two sessions. My name is Mohit. I originally belong from the land of the abundant sun and now live in the land of the hiding sun, Seattle. So it's good to be here in Boston, but I'm sad that clouds have followed me up to here. No user left behind. I will start with a story. A long time ago, in a galaxy far, far away, believe it or not, there were hundreds of users who used Bing to browse the internet on a regular basis. They used it on a regular basis, but then, after a few weeks, it just stopped working. They tried for a lot of time, and then they eventually gave up. Fast forward to a few weeks, and then an employee from Bing just happened to be in the area near the Amazon. He noticed that Bing wasn't working either, but he had the luxury and tenacity to figure out what was happening, contacted customer support, reached out to us. And it did not take long for us to figure out there was something funky going on at the ISP. So we started getting in touch with them. What took long was getting a response back from them. After multiple tries and multiple pings on their first public Facebook page, we finally got a hold of them. They fixed it. It turns out that they had a proxy that was dropping egress traffic back to our origin. And you might ask, like, what was a proxy doing on an ISP? That's a different question, different battle, different day. But for now, they fixed the problem, and everybody lived happily ever after. Not everybody, though. Some users we never got back. And the question that we had was, is there someone else who goes through that same experience? And is there a way we can know when it can happen? That is a question we are trying to answer. So I want you to take a couple of, not a couple of minutes, but 10 seconds to answer this question within your minds. What do we as engineers want from monitoring? And think about it yourselves, 10 seconds, no need to answer it aloud, but it is very important for us to understand. After spending hundreds of millions of dollars on a product that we build and design, all we want is to ensure users get the intended experience that we designed for them. There are two qualifiers in this statement. One is the experience itself, and that can be classified by the performance that the user sees and the quality of the service that you present to him. The second and more important qualifier, in my opinion, is getting to the experience itself. And getting means two things: availability and reachability. So availability reflects the state of the services themselves. Think of availability as something that focuses on the serving stack. It is the equivalent of measuring how often a customer is successfully able to hear the dial tone when he picks up the phone. That is where you get the concept of dial tone availability, right? However, reachability is a measure of success of how the user is able to pick up the phone itself. In an analogy, reaching for the phone is reaching and making a connection to us, and picking up the phone would be making a successful TCP connection. So that is reachability from our opinion. The next question is, why? Why should we talk about it? Is it a topic worthy of discussion at all for 45 minutes? And more importantly, why is Bing so interested in it? What is in it for us? We are not an ISP, but why do we care? Number one, is reachability a big problem? Not really. And the reason is, think about it like that. Think about a glacier and its monolithic, stable system. And from a high-level point of view, it looks perfect. But when you look underneath the surface, there are constant fractures and fissures going on. And if you happen to be at the wrong place at the wrong time, chances are you'll be at risk. So reachability does exist to be a problem. And it is not just we who actually see that. Actually, I was reading this article probably 4 days ago where there was an interview by Casey Rosenthal, who manages the traffic team at Netflix. And I totally agree with him that there are some big problems at ISPs and some that would actually make some interesting stories to read. So what we decided and concluded was, yes, it is something that we need to solve. Next question that I talked about was, why should Bing care? And the reason is, we are a stateless service. What do I mean by stateless? From that sense, your HTTP request for a search query a few seconds from now can be on a totally different search engine from the search query that you gave a few seconds ago. It doesn't really matter. In the business of search engines, the context is dependent on the user. They have it on their brain. And a search request is just one request, one response, and that's it. The ability for a user to have patience is extremely low. There's another factor. There is no specific economic network effect in place as such in the generic business. So there is no vested interest for a user to come back to the same search engine, except the quality of the search results, of course. And there is no social network around it. So it behooves us to make sure that we are actually reachable by the majority of our customers. So I have a question for you. How many of you have customers who are real people? What I mean by real is not us. We are not real in terms of that. Like real people outside who walk on the streets who are not into IT. Show of hands. Okay. And you might agree with me in some way, and that users expect us to own the entire end-to-end experience. They do not distinguish between DNS services, ISP, your CDN, or your endpoint, whatever that might be. At the end of the day, there are a bunch of websites that work and the ones that don't. If your competitor happens to be on the one that does, and you did not at that point in time for whatever reason, you just lost a user behind. So we need to work on that. Measuring reachability is a very hard problem. And traditionally, the way we do it in our monitoring circles is we do external synthetic monitoring of various sorts. And it's a good thing. It covers two aspects. This is, I got this something from Donald Rumsfeld, its famous speech. He talks about known knowns and known unknowns. So what happens is there's a kind of outage that both users and us know whenever we have a major outage. External monitoring does catch that. There's another kind of monitoring that the user does not realize, but we do, which is our failovers. If we have a system designed correctly, it'll be able to follow up and determine what's happening. There are two problems that it does not detect. And those are the variety that I talked about in the story in the beginning, where users see a problem, we do not. And the other is a very interesting one, which is users and us are equally unaware that something funky is going on, and we are not seeing the traffic come to us at all, but the user believes that he's coming to us. So those kinds of issues are something that we need to work on. External testing alone as a measure does not work. It is prone to the false positive paradox. And what essentially that says is, if you have a highly reliable test with a false positive rate of 0.01%, and you deployed that test across a bunch of nodes and iterated many times over a period of an hour, the probability of getting a non-trivial number of false positives is extremely high. So that means it's not a dependable thing. The other problem with external testing is the low coverage of user base, especially for us, because we have users in almost every city in the world in some way. So what happens is, when you look at the locations that an external test provides, even including last mile, it is merely a subset of where our users are. And it's not to say that we should make the external testing system scalable. It is not. It is impractical. But it is just a shortcoming that it exists. The final and most important one is, it is not actionable on a single failure. And maybe some of you have gone through this, but if you got a call at 2 o'clock in the morning and a single test in a single node in South America failed for 5 minutes, you got up, you checked all the metrics, everything looks okay, chances are you will succumb to your bias and say it is a false positive or a false alarm. I'm going to take a look at it in the morning if it's a problem, and then move on. So it might be a real issue, but you just decided to go forward, and I cannot blame you for it. Math says the chances of it being a false positive are really high. So we need to make it actionable. What does it really mean to us? It means having the data or the means to fix the problem. And if you look at the statements over here, you will see that the specificity of the geographic location and the network increases as we go down. So does the confidence in our predictability. and also the number of users affected. So there are 3 attributes that we call important for actionable data: approximate impact, the degree of confidence, and one of the most important things, the coordinates, which is where did the problem happen and what am I supposed to fix where. So coordinates is a tricky one. And if it's a tricky one, I have a fancy name for it. It's called the Reachability coordinate system. It basically just means we need to know what the location of the user is and the AS number to which the IP address belongs. AS numbers are pretty simple, if you understand IP, and they have to belong to an AS. Leaving complex scenarios aside, you can trust the data and you can figure out what AS they are on. Today, the Rev IP system is good enough. You can look at an IP address and figure out what geolocation the person belongs to. If you look at cities alone, cities are too damn small. There are 20,000 plus cities in the US alone. Using that as a dimension does not really work. You will be working with so many false positives, you will just die of old age immediately. States are too big. And the reason they're too big is if there is a small ISP in the state of Texas and it had a problem and you detected it, what are you going to do? Call them and say you have a problem in Texas? It does not really work. So metro areas sound just about right. And metro areas are nothing but a cluster of closely positioned cities that are distinguishable from each other as a cluster, and that just works. We wanted to look at commercially available or openly available metro systems. The problem is they are mainly focused on the US and do not scale internationally. So what we had to do was reinvent the wheel in some way and come up with our own metro areas. And metro areas are where our users are. And that is a function of population, geography, and volume. And what they are essentially is this cluster diagram of the representation of the entire world based on the function that I just spoke about. And new regions are extremely easy to add. There is a classifier that runs and finds out the nearest neighbor and puts it in there. And changes can be done very easily as well. The beautiful thing about something like this as a cluster system is it scales internationally. It allows us to draw our own boundaries based on where our users are, which is what we care most about. It allows larger areas to become to have sparser regions. So that if the population density in Canada is extremely low in the upper areas in the northwestern provinces, 2 or 3 provinces will be collected to form a single cluster because that is the amount of traffic we get from them that is identifiable. For what it's worth, actually I have to show you this. The US has about 220 metro areas according to our distribution. So if you look over there on the top right, I never expected the quality to be so bad on the screen, but that is the top 25 metro areas that we thought were there. And if you look at the graph below, at the map below, that is a cluster of California zoomed in based on the programmatic way we discover clusters and regions. And if you notice, it looks pretty intuitive. There's a Bay Area, then there's San Francisco, and there's Los Angeles, and so on and so forth. So what we discovered was it was possible to use a programmatic approach, divide the world into the system that we want without working through counties, districts, and whatever that might be, and actually do a good job. Next was coming up with a model solution to figure out what needs to be done after we get this coordinate system in place. So our model essentially needs to produce an outcome, which is an alert of sorts, which says, go, something is bad, fix it. The outcomes that we want from this particular model is a relatively high recall. And recall basically says a low false negative rate. And the reason we cannot aspire for an extremely high recall is because that problem will continue to exist. We just assume that it will never be fully discovered. What we can aspire for, though, is 100% precision. And precision really means extremely low false positive. We do not want to wake somebody at 2 o'clock in the morning unless there is a higher problem. What I have seen in a lot of monitoring systems is we do not use these 2 metrics to determine how effective they are. They are extremely useful to figure out how you can make lives easier for developers. The model has to be statistically defensible, capable of learning, and should be fast. Signals are the input to the model. What we want the signals to be is to be a proxy for users. They have to, or they can be representative of the state of the internet itself. We ask 2 things. Number 1, they should be aligned to metro ASNs in some form so that we can look at our data dimensionally. And the other is it should be on a time scale so that we can look at changes over a period of time. Those are the only 2 things. Okay, so let's look at the signals, because we already discovered what the metro ASN pairs, our coordinate system is. We already know what our outcome should look like in terms of decision-making approach. Now we need to know what gets fed into the model itself. And there's quite a menu over here. So these are the way we divide our signals into deciding what's going on. It looks difficult, but it's fairly intuitive. Direct, which is basically deterministic testing, external synthetic agents. Indirect is relatively new, which is app-based telemetry, where you have an alternate telemetry endpoint, where an app can inform that endpoint that your primary service is unreachable. Hockey app, Flurry are some examples that come to mind. There is another one which is called the network or navigational error logging draft, which I will talk about later. It's very close to my heart. Inferential signals are the most important. They are measurable from inside a data center itself, and that is detecting traffic drops. Correlational, as the word says, they correlate. The thing with correlational is they are not harbingers of a problem that is happening, but they support or do not support a problem that you see in the system. So if you see a traffic drop and if you see some social activity, then you think that it's really a problem. So that is how they're useful. Causal signals are coming that are emitted from the core system itself. BGP might tell you that something broke. It is a good signal to have because you already know the root cause. You just need to figure out now what broke because of this change. So that is how BGP signals are used. So anyway, so we'll go into more detail later. Done with the signals, done with the pairs, outcome done, model next. Okay, so how many of you like playing games? Not the mental games that people play, but computer games. Show of hands. Okay, so you might find this slightly amusing because to make this more fun, what I did was I decided to make it a game itself, and the goal of this game is to bring down this monster called Metro ASN with the most potent and the minimal number of hits that you can present to it, that you can attack it with. So there are a bunch of signals that are going to attack your monster, and if your monster dies, it triggers an alert of sorts. And the goal of the game is to do it in the minimal number of signals with the maximum amount of intensity. Simple gaming kind of a system. So of course we had to have attributes, just like any other Pokemon kind of a thing. So there's strength, that is the intensity of the attack itself. Health of the signal. The health, okay, but I'll talk about health in a bit. Skill level, that is basically the precision of the signal as to how accurate it can be. The power of the signal, extremely useful, which we'll talk about in an example later on. And the recharge time. Recharge time is how fast or slow does the signal or the monster take time to recover all its energy or strength. So if you look over here on the right hand side, once the health goes down to 0, if the monster started with 100, once it goes down to 0, everything looks good, and then an alert can be triggered. That is how the system would work. The formula below, I don't know why it did not delete it, but yeah, if you're interested, maybe it's a simplistic way of looking at the way the model would calculate. The one thing over here is the health for the signal. Monsters cannot attack signals back. However, we tend to reduce the health if the signals have not been good boys and good girls, in the sense that if they have a lot of false positives, we reduce their strength, or we reduce their health, so that they do not have the same capacity that they used to have to hit some Metro ASN back. I'm hoping it's all clear so far. Let's look at an example of a direct signal. External tests. We use synthetic testing from systems like Catchpoint and Dynatrace. They do not alert users directly, or users as in engineers directly. They go into our system. And that is because the outcome of the system will decide whether that alert is worthy enough or not. Last mile testing increases coverage, but at a cost. So it depends on how much you want to add that. And top 50 Metro ASNs and a bunch of others are easily covered. What you will notice here in this sample for the New York, Brooklyn, Bronx Cablevision Metro ASN is the strength is 50. What this means is it'll take 2 hits from the signal to kill that particular Metro ASN pair. Not a single test failure is not going to do anything. You might have questions about it, but we'll talk about that later. Next signal is correlational, Twitter as an example. And simple sentiment analysis, I hope Lord Waters is happy. Simple sentiment analysis over here, it looks for known negative words. Also overall mentions. It is loosely based on anomaly detection as a system. The thing is, so far we haven't put geo data into our Twitter feed, so it is low strength. If you notice the strength number, it is 10. There is no association with metro ASN, but the moment we have it, the strength should go up. The problem with it is highly prone to feedback and opinion spikes, and what that means is if a homepage was liked a lot by users, people spike in Twitter about liking the homepage. If they don't like it, they say some other things. So what happens is we are not able to distinguish clearly between positive and negative sentiment that well. That's a lot of work in progress, but a lot of work to be done. So again, a correlational signal. Last signal I'm going to talk about before the rest of the stuff is inferential traffic drops. And this is absolutely the most important. It uses anomaly detection. We use Twitter's open source ESDR library. That we wrapped it around with our own stuff to make the outcome more reliable. And what we did was we added a damping calendrical signal of sorts to account for holidays. And what I mean by that is power. Every country has its own set of holidays, the way it celebrates. And when you look at traffic anomaly detection, it has to look at a previous signal to determine what happens next, right? And holidays can change. Some people have lunar calendars, so it's not possible to determine what day that thing is going to happen. July 4th is easy. Other holidays are not. So a signal as a power determines additively or subtractively what we are going to do with the strength of the signal. Drops in traffic are classified as egregious, large, or medium, and that is reflected in the skill level for the signal. You will notice 0.25, 0.75, and 1. And there are 3 graphs over here, and those are here to just show that how the pair really helps. The first one is just a complete metro area for all the traffic that came into the Philadelphia region, and we could not detect an anomaly over there. Then the second graph is for an ISP that serves the same region, among others, and we could not even detect an anomaly that side either. But the moment we paired both the metro area with the ASN as 2 X and Y dimensions as such, we were able to determine the anomaly and figure out what was going on. All right. All of that is okay, but there's no fun without simulations because reachability issues don't happen on a day-to-day basis, so we decided to take some real data, inject some faults into it, and then we decided to see how did our model work. Scenario number 1, just one test in metro ASN pair 3 fails. Ignore the quarter rank and the annual rank columns. They're just to make sure that if there's a bunch of alerts that happen, what should you look at first? The highlighted column shows that once that direct hit happened, the monster was only hit by 50, and it's only reduced by 50. What happens after 15 minutes and the test fires again? Lo and behold, we do not see any increase. It just stays 50 again. And so what we saw was single node failures with no supporting signals except direct test failures don't cause false positives. And this is happening because of the recovery time. The monster recovers faster than the external test itself. So the external test does not have the strength to kill the monster on its own. It needs help. All right? So that is what A is. All right, so if the metro ASN3 failed, but there was a 50% traffic drop as well, what would happen? Very simple, intuitive. You add the traffic hit by 50%, and the strength is multiplied based on the model, and you get a number which is in red. Assume it's over 100. It's 125, I believe. So you do that, and what you see is 2 supporting signals reach the threshold really easily, and you're able to detect a problem. However, in real life, networks don't go down just in city dimensions. They tend to bleed over because that is not how a network is laid out. So let us try to see what happens when a single network fails in our simulation and what the model does. So say network ID 7 has failures in a lot of metro areas, and somebody complained on Twitter as well. You will notice that the Twitter column is 10 in for everything. What that means is we do not have geodata yet, but we'll add that soon later. Direct hits are there only for 2 metro ASNs pairs, and the traffic hit varies based on the metro AS. There is one at the last which says 25. That means some users were affected, not a lot. And what we see is external test regions were the only ones that actually triggered. So if it was not for them, we would not have discovered this problem that soon. So they are the reason this became a true positive. So they are extremely important. However, what would happen if the external testing system was not in place? So that is our last scenario. When you look at the simulation, the metro ASN7 has a medium drop in traffic. No external tests or reports have been made. So there is a 50-point damage to the monster. And now, what would happen after 15 minutes? We see that the threshold was crossed easily in the model, and the reason is a sustained traffic drop is treated differently than a sustained node failure, simply because of the way recovery is made. A signal based on inferential traffic drop recovers faster. A signal based on external testing takes a longer time to build its strength up. So there's one thing over here. We knew in 2020 hindsight this was a problem, so we actually had a longer time to detect. We could have detected in the beginning, but in the interest of avoiding false positives, we decided to make sure that a longer TTD was useful as long as the impact wasn't extremely high. All right, so these are all the scenarios that we played in simulations. The question is, what did we really find in the wilderness outside on the internet? And quite a few things. Multiple DNS hijacks across ISPs, can't even imagine, even in the US. It's a pain in the ass to fix them. DNS hijacks are a very sensitive problem, but it is absolutely a bad experience for users. Classic example, the South America story I talked about. So yes, we caught a bunch of them everywhere, still working on it. Reachability impact due to fiber cuts. Traffic does reroute, but at some point in time, there's a small segment in time, maybe seconds, when people actually, because people are looking for things all the time, so you can actually observe the drop, and you're like, why the hell did this happen? And then it correlated with an RTT spike, so you figure out that something happened, and then you figure, okay, you can deduce that something happened, and you discover fiber was cut. A school district blocked us because they were still having our older domain name live.com on their blacklist for some reason. We had to update them, and once they updated using their firewall provider or whatever that might be, everything started working again. So, but these are the kinds of things we were finding. Another BGP hijack event happened in South America. This was a much smaller one, thankfully, but we were able to catch it. And within like 6 hours or something of that sort, because it was a very small place. Then we also found an unusual day when a particular government agency took half the day off, and we never expected them to, but the traffic just fell down, and we never knew that offices behave that way. Everybody knows when somebody leaves an office building, traffic would go down, but when the whole department of X goes away, hundreds of, thousands of people, you see a drop on the network, and we thought it was a real problem where somebody blockaded us again, but no, half day, whatever, good job. So, a lot of problems. What doesn't work? Lots of stuff that needs to be done. Existing issues become a part of the baseline, become a part of the Borg. So no modeling for our calendrical system. Right now, the calendrical system I talked about for the US holidays and all that is, I just hand type it and make a jiggly, square wave pattern of sorts, and I do it. I want a way to ideally maybe have the calendrical system be programmatic so that countries can do it automatically, and we have the corpus to do it. We just need to spend time. Third is extremely important. The only question is like, okay, so you saw a traffic drop. The next question is it a Bing outage, or did the ISP really have an outage? And if the ISP had an outage, not that we don't care about it, but we basically have to fix it and find out what's going to happen. Extremely low signal to noise ratio. We're going to work on that and see that if we can buffer the amount of traffic so that our predictability for smaller areas becomes better. Feature DSAT can be pretty hard. We already talked about that, how Twitter can screw up things. Reverse IP data chain, that was an interesting one. Bunch of /22s and /23s went missing from a certain area. We could not find them. We figured out because we were only looking for drops and not spikes in traffic. We thought they had gone. What happened was the Rev IP data changed and put them from state of Texas to state of Massachusetts or something like that, and we could never see that. So anyway, learning lesson. Escalations. So yeah, time to detect improved, but users don't care about time to detect. They care about time to mitigate. How fast you can get them back. That takes a lot of time with network teams, especially with far off ISPs who do not have a proper NOC in place. Wish list. I'll skip a few, but indirect signals is the most important one. So app-based systems have these things called Hockey app and other systems that can send you offline telemetry. There was this draft in the W3C system, which is called network error logging. It has the capability for the origin to send an alternate telemetry endpoint via a policy update using HTTP headers, so that if your website is inaccessible, it'll send telemetry to your alternate endpoint, letting you know that your website was not working. So that is an extremely valuable thing for owners, website property owners to have to figure out what's going on. We want to fix the Bing outage versus ISP outage problem. We have an idea, maybe using something like Sedexis. Make a plugin-based system. It's a hack. We need to fix that. We need to make it a proper product if possible, something that we can see. And we need to build a better learning model for seasonality. Takeaways, if you've been here so long, you should take something away. Assume that for large consumer services, someone is having a problem just with your service as you sit over here. You have to assume that, and that is how you have to behave in order to capture these problems. Especially for a large stateless service like ours with extremely high churn, reachability becomes extremely important. External tests are not the complete story on reachability. And there's power in unity of different signals. Signals are everywhere. We need to understand what they tell, what story they say, and you make a composite out of them. It is possible to get action out of a composite signal rather than individual ones. The last is a typical educational one. Anomaly detection in machine learning can play a large role in monitoring. Anomaly detection is, to a large extent, but we tend to work within the bounds of moving averages versus standard deviations and the stuff, and there's a little more that we need to do around it. And when I say machine learning, it's an overloaded term. Everybody talks machine learning. I found out later that clustering was machine learning. I did not know that. So anyway, point is machine learning and anomaly detection are something that we should actively focus on and see if they can help our lives. So thank you for listening. And if you actually had the 30-minute nap, you can thank me for that. Thank you. Questions?
I have two questions. I'm Craig Jackson from EBSCO. First of all, sort of how do you get off what tools do you use to do the traffic detection by ASN? Do you have some tool that listens to the BGP feed, and do you do it at the application level of?
We do it at the application level, and the reason is the BGP level. Microsoft is huge. We wanted to see how Bing works, and the ingress is all for Microsoft is a single place. So we looked at Bing at an application level. What we did was we have real-time streaming of data. We look at all the IP addresses, break them by /24s to anonymize, and we have TTLs on that. And what we get ultimately in a few minutes is the AS number. We discard the IP. We just need the AS and the location. And the location that we use is just a city, and that's what we use.
But so you just sort of snap it periodically to see where this.
Actually, not periodically. Yes, in a way, periodically it happens every 30 seconds.
Okay, so you have an up-to-date bit.
Yes, absolutely.
And do you at Bing encounter any unusual networking situations? At EBSCO, we've had problems with research networks.
Okay.
And where we have special routing that goes because we're subscribed to this network and they're subscribed to this network. We route over this other network. And
so, are you having problems reaching me, or like?
No, I mean our customers are having problems reaching us.
Okay.
Over, and we have like an outages. All the universities in Quebec can't reach us.
Yeah.
And
trace routes are the only thing. Ingress and egress trace routes.
Yeah.
This is what I usually end up like. We were lucky for the South American incident because an employee was there. We asked him to run a trace route from inside the ISP.
Okay.
Because the ISP wasn't responding. Otherwise, we couldn't have had the data to show that you guys are.
Okay, so you haven't, because that's been one of our problems.
Absolutely.
Is that particular networks that are particularly poorly managed.
Yes, absolutely. Yeah, you're right. Thank you.
So when you determine that one of these metros is having issues, it's kind of two questions. One is, how do you shift traffic away from the affected, or maybe it's like a partial, maybe they can only not hit some of your edge locations, or is this like an entire?
So it's an inverted problem. It's not a problem where the edge cannot reach out to the customer, and basically the thing is, there is no statefulness in the system. There is no way for us to tell the consumer, go to another place.
Okay.
Right? So especially with our system, anyway, so yeah, I won't go there, but we can talk about it offline. What happens is we have to assume that the user has no capability to even detect that a DNS change happened. Say there were 2 A records, the first one failed. The problem is the way DNS protocol, the way the browsers work from a multiple A record point of view, the TCP connection has to fail, and then it has to move to the next A record automatically, right? The problem is most of the proxies send the fast TCP back, already handshaked, back to the browser. So the browser is expecting everything to work. It does not even go to the second A record. So everything just fails right there.
I see. Okay. Okay, thanks.
Hi, I'm Nikolai Plum from Booking.com. Thank you for the talk. Regarding Brazilian ISPs, I also have experience that they are not responsive. Regarding monitoring by logging data to some host that isn't on your network, we've also tried that before the proposed standard you mentioned. And we also found very interesting things where our network was not reachable from some places due to peering issues or whatever.
Yep.
So my actual question is, regarding events in calendars and so on, how do you handle sort of shorter duration events? Because, for example, during the World Cup, when the match is actually on, we see a very sharp traffic drop.
Yeah.
And sometimes events can also be unpredictable. For example, evacuation of a large area because of incoming natural disaster or something.
And I've thought about that. So the problem is the current calendrical system that we think about is based on days. We thought about taking a newsfeed approach where we look at a newsfeed. Because we are a search engine, we have news data.
Yes.
We can figure geolocations from where that news is emanating and then figure out. However, we haven't been able to do anything of that sort yet because it should be done, but we should do it.
How much of your false positives is due to that problem and how much due to other things?
Because we're not looking for those problems, that becomes a false negative of sorts, if you can call it that. Because if for example, if there's a match going on and there was a spike in traffic, but there was a problem at the same time as well, right? So the traffic dropped, but it did not get detected as an anomaly because historical patterns did not change. So I've seen a couple of those incidents where a spike was there, but we did not see it. And it takes time for the system to learn. It'll take a complete year to figure out what's going on. And I can give you details later, but what really happens is in spikes, the system does not behave the way we thought it would in traffic spikes. In drops, perfectly fine. But like a classic, when Michael Jackson died, there was a huge traffic thing. And if our system was present at that time and we had an outage with 30% traffic gone, we probably would have missed it because it still looked normal.
Right, okay, thank you.